last time we derived an expression in blackbody radiation for the mean number of photons with frequencies between omega and omega plus d omega. Just to remind you, we were starting, when we were talking about frequency, we were using f, but omega is just 2 pi times f. Probably have figured that out by now. In any case, so my expression looks like this. It's 2 for the number of modes, 2 transverse modes. This is telling me the mean number of photons with frequencies between omega and omega plus d omega. Now, what I would like to do at that point is to say the mean energy per volume, or what we call the energy density, little u, is going to be the following. I can write it in terms of k, 2h bar omega, f of k, 4 pi k squared, dk, or write it in terms of omega as 8 pi h bar over c cubed, f of omega, omega squared d omega. So this is the energy per volume. So if I want to find I can then put in my expression for the photon distribution or Planck distribution. If I do that, I have an expression for energy density that looks like this. Now, of course, what I would like to do is know what the total energy is. So what I need to do is integrate this expression to find the total energy. The way we do that is to make a variable substitution. I'm going to use eta, define eta as h bar omega over kt. That's going to change. My integral is going to look like u of t is equal to the integral 0 to infinity h bar over pi squared c cubed kt over h bar all to the 4th eta cubed d eta over e to the eta minus 1. Okay, so this is the expression we have to integrate. Most of these obviously are constants. Eta is the only variable involved. It's actually quite easily evaluated. The integral, if I pull all these constants out and I evaluate this integral, you can go to the appendix of most statistical mechanics textbooks. The value of that integral is pi to the 4th over 4. So my expression becomes u of t is equal to pi squared Boltzmann's constant to the 4th over 15 c cubed h bar cubed t to the 4th. This is what we call the Stefan-Boltzmann law of radiation. This was predicted by Boltzmann in about 1884. It was empirically arrived at by Stefan in about 1879. Oftentimes we express the law as a constant. This is what we call the Stefan-Boltzmann constant times t to the 4th. What it says is that the energy is proportional to the 4th power of temperature. And of course, sigma is a constant defined as the Stefan-Boltzmann constant, pi squared k to the 4th over 15 c h bar quantity cubed. As I say, this was empirically determined in 1879. Boltzmann explained it, or was able to derive this t to the 4th dependence for energy in about 1884, but it took the work of Planck to arrive at this, the whole theory behind this blackbody radiation law. So he was able to, A, solve the blackbody radiation problem, and he was able to then also begin in some way set the foundation for quantum mechanics that would follow in 20-some years, along with Einstein and the photoelectric effect and other things. Other things we can get from this, by the way, we can calculate a heat capacity, which is just the derivative of the energy with respect to temperature at a constant volume, and that will turn out to be 4 A T cubed, where A is 8 pi to the 5th K to the 4th times volume divided by 15 HC cubed. And this works all the way down to T equals 0. Of course, the T equals 0 is heat capacity is 0. Entropy can be expressed as an integral of the heat capacity, 0 to T, CV of T prime, dt prime over T prime, and that's going to be 4A 0 to T T prime squared, or 4A T cubed over 3. Put it all together, the entropy can be written as 32 pi to the 5th over 45 times the volume, KT over HC cubed times K. So you can get expressions for heat capacity and entropy following the work for the black body radiation. The last point I'd like to cover in this topic is sort of a really great application of black body radiation. That was in the discovery of the cosmic microwave background. And you might recall the story of the two Bell Lab scientists who almost by accident discovered this radiation that I thought was static in their radio telescope in Holmdel, New Jersey. This is 1964. What they realized, though, was what they were, the radiation that they were detecting indicated that it was, that the wavelength of the radiation they were detecting indicated that the temperature of that radiation was about 2.73 Kelvin. So the temperature of the cosmic microwave background is about 2.73 Kelvin. This is left over from the so-called Big Bang, left over from a time when the universe was filled with ionized gas that interacted very strongly with electromagnetic radiation. And you have to be a little careful because that's not an equilibrium situation. Nonetheless, the statistical mechanics still applies fairly well. The temperature at that time was probably about 3,000 Kelvin in the universe. But because the universe has been expanding, you figure about 1,000-fold expansion in all directions. By that time, the photon wavelengths are heavily Doppler shifted, such that the effective temperature would be about 2.73 kelvins. And if you look at the so-called black body spectrum for that cosmic microwave background, you find that the peak, the wavelength at which it peaks at is on the order of 10 to the minus 3 or so meters. Now, far infrared radiation doesn't penetrate our atmosphere. So what we're seeing with radio telescopes on Earth is maybe just the tail end, that tail end of the spectrum in the microwave region. And that is what we attribute to the so-called Big Bang and the expansion of the universe. So you have some pretty far-reaching implications and applications of the Planck black body radiation law. Thank you.